Good afternoon, everyone. This is Jappy, and today on our first YouTube video, we're gonna be solving under differential equation, first order differential equations, type of variable, separable equations. Okay, so in this video, I hope or we hope to solve for separable equations are courtesy of these 4 problems, and I hope that you guys will learn from this video as well. Let's start. Okay, so for our first example, is a very easy example. dv over dp is equal to negative v over p. Okay, so on our first example, we have two variables, v as the dependent variable, p as the independent variable. And take note, okay, in variable separable equations, we need to separate each variable into its own term. Or we separate each variable to its own side. For example, we multiply this equation to dp over negative v, so that our dv will have negative v below is equal to dp over p at the right side. Now that they are separated by the name itself, variable separable equations, the variable are separated on its own side. We can integrate them. We can integrate them, each variable separately. Integrating the left side, we will be having negative ln v. On the right side, positive ln p. Okay, so under differential equation, we are required, or it is prerequisite, that we know how to integrate variables. Plus ln c. We can use c or we can use ln c when integrating equations in differential equations, but since v and p are both in natural logarithm function, or ln v and ln p, so we're gonna be using ln c for our arbitrary constant. Then basically we're gonna be like simplifying. Okay, we're gonna be simplifying, so we're gonna be like moving p to the left side. We're gonna be having negative ln v minus ln p is equal to positive ln c. Okay, so now that the v and p are both on the left side, they're both negative. By a property of natural logarithm, we can simplify the equation into this. Okay, and with ln on both sides, we can raise both sides to e, having the equation of vp raised to negative 1 is equal to c. If we square both sides, okay, if we reciprocal both sides, we can have vp is equal to c raised to negative 1. And then, since c is constant, we can let c raised to negative 1 equals to c, okay, for simplification purposes, so that our equation will be simply vp is equal to c, which is, this will be your final answer. Okay, so take note, for simplification purposes, we're doing this in order to simplify our equation, to make it cleaner, to make it more simpler. Right? Okay, now that we have solved for number 1, this is number 1, we're gonna be solving for number 2, which is number 2 is x squared y prime is equal to a raised to y. E raised to y. Okay, a raised to y. Okay, so that's superscript y. So again, for separable variables, we need to separate both sides. And in order to be able to see it clearly or solve it clearly, we substitute y prime with dy over dx e raised to y and multiply both sides of the equation to 1 over x squared. To eliminate x squared on the left side and move it to the right side, multiply it to dx, same, and divide it by e raised to y. Doing that, we will be having the equation of y e raised to negative y dy is equal to dx over x squared. Okay, so we have two different terms now, one of both y and one is x squared or x raised to negative 2. Okay, so if we integrate x raised to negative 2, that will become x raised to negative 1 divided by negative 1. Okay, so that is much simpler than the left side, which the left side is y multiplied to e raised to negative y. There's two variables. So we will be using integration by parts, meaning we can use the integral of y means uv or udv. The integral of udv is equal to uv minus the integral of v du. Okay, my suggestion is always use the term or let u, the term u, be the simpler variable, which means y. Du is equal to dy. Then whatever the rest is, usually that's the case, right? Whatever the rest is du, okay, or dv, sorry, dv. Whatever the rest is dv, e raised to negative y dy, and the integral of e raised to negative y dy will be e raised to negative y divided by negative 1. Divided by negative 1. Okay, what's next? We substitute that values. So meaning the left side here will become, it will become y multiplied to e raised to negative y divided by negative 1, it will become negative, minus the integral of v du, meaning negative e raised to negative y, the v, and du dy. Okay. This one, v du. Okay, that's the whole left side using integration by parts. Next, on the right side, the integral of dx over x squared. Okay, integrating all the terms, we will be having negative y e raised to negative y, positive, negative times negative is positive, but the integral of e raised to negative y will become negative e raised to negative y is equal to x raised to negative 1 divided by negative 1 plus c. Okay, we did not use ln c because there's no term having the c value here. Okay, there's no terms having c. Okay, sorry, having the ln or natural logarithm value here. Okay, now we simplify. I'm gonna put all the positive on the right, all the negative to the right side, so it become all positive. Okay, negative 1x plus c plus y over e raised to y plus 1 over e raised to y. Okay, we now are gonna multiply this by e raised to y and x to eliminate the denominator. So this will become e raised to y negative plus x e raised to y plus xy plus x. Okay, so I'm gonna be c on the e raised to y on the second term. Okay, we forgot. Okay, so I'm gonna separate e raised to y. We will now be having like e raised to y xc minus 1. Okay, these two, there's two terms. Okay, plus x, both term having x, y plus 1. Okay, is equal to 0. Okay, this is now our okay, this is now our general solution. We could solve now for number 3. For number 3, what problem do we have? Tangent square y dy and sine cube x dx. For number 3, we have tangent square y dy and sine cube x dx. Okay. So notice on this problem, both the terms have been already separated, or it's already separated. The y variables are already on the y on the left side, and x variables are already on the right side, or on the x term. Since the equation is already separated, we can be proceeding, or we can proceed into integrating both terms. Unfortunately, both terms are a little more complex, or there's no direct integration on both terms. Okay, so first off, we could use trigonometric identities. For example, okay, we know that sine square theta is plus cosine square theta is equal to 1. See, then sine square theta is equal to 1 minus cosine square theta. We simply move cosine square to the right side. Then tangent square theta, which is tangent square or tangent is equal to sine theta over cosine theta. Since it is squared, sine square theta over cosine square theta, the top will be equal to 1 minus cosine square theta. Okay, this one. We simply substitute that at the top. Okay, we have tangent y dy. So in order to integrate that, I will be substituting the tangent function with its identity, cosine squared theta. I will be substituting with its identity, which is secant squared theta minus 1. Okay, we have like 1 over cosine squared theta minus cosine squared theta over cosine squared theta. Okay, so meaning tangent squared theta is basically secant squared theta minus 1. Tangent square y is equal to the integral of secant square y minus 1. Parenthesis dy. Okay, now secant square y has its own direct integration. Okay, if we're gonna be continuing on the left side, the direct integration of secant square y is tangent y, and the 1, negative 1, the integral of negative 1 is negative y. Okay, we will not be putting c because we have not yet integrated the right part. For the right part, sine cube x dx, there's no direct integration of sine cube x dx. So in order to lower the degree of our trigonometric identities, I'm gonna be separating the square from the cube. Okay, so sine square x multiplied to sine x is equal to sine cube x dx. The integral of that, there's no direct integration yet, but sine square x is equal to 1 minus cosine square x multiplied to sine x dx. Okay, simplifying this further, we will be having the integral of sine x dx minus cosine square x sine x dx. We have two terms that needs integration. Okay, so the integral of sine x dx will become negative negative cosine x. The integral of sine x is negative cosine x. And the integral of cosine square x sine x dx, we now can substitute. Let u is equal to cosine x, meaning du is equal to negative sine x. Okay, dx. Okay. So this last term, the last term, negative sine x dx cosine square x, is basically u squared. The cosine x is u squared, while the negative sine x dx is du. And the integral of u squared du is u cubed over 3. Okay. So the integral of that is positive cosine cube x over 3. Positive cosine x cube over 3. Okay, simplification. Let's lower down the integrated part, tangent y minus y. Now that we have integrated, we can add c either on the left or on the right. Now that, well, we can add it on the right. We can also add it on the left. It doesn't matter because it is a constant. Okay, and it's an arbitrary constant. We don't know the value, and the value changes. So if it's either negative or positive, it doesn't change its value, or it doesn't alter the equation, okay, or the general solution. Okay. Now we can put it on the left part because basically there's space here. If we put it on the right part, it's gonna be cluttering, or it's gonna clump up. Okay. Simplifying, we multiply all by 3. So in order to have just like one simple line equation, to have a simpler equation, no fraction, no radical. Okay. So if we say simplifying, we're gonna have an equation without fraction and without radical. Okay. Basically, now this is our final answer, or our simplified final answer, or our general solution. Next, number 4. Right? So I will now emphasize the word general solution for you all out there. So in solving for differential equation, first order differential equations, all the type, basically we're gonna have different type of differential equation. On these instances, we have variable separable equation, but we're gonna have differential equations. And when we integrated our differential equations, we will be having what we call general solutions. This is a general solution for number 3. This is a general solution for number 1. This is now a general solution for number 2. Okay. For number 4, what we have what we call an IVP. X, okay, let's write number 4. X is equal to 2, y is equal to negative 1. So this 2 condition is what you call IVP, or initial value problem. We usually get them. Okay, we usually use them or get them in order to have, or in order to turn our general solution into particular solution. Okay, so first let's go to our differential equation. 2y dx is equal to 3x dy. Okay, this equation feels so it's a lot more easier than the 3. Actually, I think it's the same as number 1. Okay, so let's solve for the general solution. Separate each variable into each respective term. So let's divide this by 1 over xy, so that we have 2 dx over x is equal to 3 dy over y. Integrating both terms, we will now have ln x 2 ln x is equal to 3 ln y. Since both terms are in natural logarithmic function, we will now put the c or the arbitrary constant in ln. Okay? Simplification, we're gonna have ln x squared is equal to ln y cubed multiplied to c parentheses. Okay, property of logarithm, ln y cubed or y cubed plus ln c, or let's just use a and b. Property of logarithm, ln a plus ln b is equal to ln a b. To be more specific, natural logarithm functions. Okay. Anyways, let's raise both sides to e, so we can cancel the natural logarithm. X squared will become is equal to y cubed c. This is now what we call general solution. Okay, that is now what we call general solution. And in order to get the particular solution, we need to substitute our IBP into our general solution. So our IBP is x is equal to 2, y is equal to -1. So substituting x is equal to 2, that will become 2 squared is equal to -1 cube c. 2 squared is 4, -1 cube is -1, multiplied to c. C is now equal to -4. Now that we have c, we can now substitute it to our equation. X squared is equal to -4y cubed. Right? -4y cubed. This is now our particular solution. Okay? Particular solution. Particular solutions are solutions that gives out or describe a specific line, a specific condition for our differential equation. While general solution, this is our general solution, are basically solutions or equations that satisfies our differential equation, well, generally, or it's not in a particular or a specific case. Anyways, that's our 4 equation. I hope you guys learned something from this lesson. And this is our first video. This is Jappy. Thank you so much for watching. And if you like the video and learn something, I hope you have you can take the time to press the like button and subscribe. See you guys again. Bye-bye.